Alright, here's a screencast tutorial about the solar system and our universe. So just so you know, the assignment's posted as solar system and our universe. There is 3 parts. There is the notes, guided notes through the lecture, and then there's the scale model calculations, as well as creating a physical model prototype of your solar system with household items. So let's go ahead and take a look at the tour of the universe PowerPoint. So going through here, I'm basically, you can read along and follow. I define what a planet is. So a planet, based on this definition, is a celestial body that orbits a star, which is roughly spherical and has cleared its orbit of debris. So on this note, this is why we don't consider Pluto a planet necessarily, or there's been arguments about Pluto being a planet, is because its orbit is not cleared of debris. So our planet is Earth, so approximate size of Earth is about 1.27 times 10 to the 7th meters. That's diameter. So our solar system, so we have approximately 9 different objects in the solar system, or 8 different planets. Pluto is considered a dwarf planet, so if you want to refer to the next slide on dwarf planets, basically the only difference is that they don't have a cleared area around its orbit, while a planet has. So on this note, there's 5 dwarf planets out there in the solar system, in the galaxy. Mercury is the smallest planet in our solar system, closest to the sun, and its orbit is about 88 days. Venus is the second planet from the sun. It's the closest neighbor to Earth. It's the brightest object in the sky that we see, and sometimes looks like a bright star in the morning or even in the day, and it's a little bit smaller than Earth. Earth is obviously the third rock from the sun. That was a pun on the TV shows. So it has about 70% of its Earth surface is water, and there's an atmosphere which allows for life. So the Earth also has a moon that rotates around it. So this kind of gives you the moon phases around the Earth as it rotates. As Earth is rotating around the sun, we also have moon rotating around Earth. And then Mars is the 4th planet. So it's the one we've sent the most spacecrafts and rovers to pretty much see if there's any aspect of possible life on other planets. So here's kind of next after that we have an asteroid belt. So the asteroid belt, click on the link. It's the torus-shaped region in the solar system between Mars and Jupiter that's occupied by solid irregular shaped bodies such as asteroids and little minor planets. And then next is Jupiter. So Jupiter is the largest planet in our solar system. The spot is known as the red spot. You can click on this link for more info about it. Saturn, then Uranus, and Neptune. So Pluto is a dwarf planet, as we said earlier. And so these orbits, we realize that as they orbit around the sun, they're not actually perfect circles, but the orbits are elliptical, and so the orbital period or time it takes to go around the sun is related to the radius, or the radius of the planet is from the sun. So the Kepler's law is period squared equals radius cubed. You kind of take an average radius because they are ellipses. The Kuiper belt, this is not to be confused. It's the one outside of Pluto that has pretty much not to be confused with the other the asteroid belt in the middle of Mars and Jupiter, but this is the one that's outside. It's truly a frontier, and that's where we're still kind of just beginning to explore the space. So this is looking at pretty much the relationship between how far away things are from our sun, and what comes next. Relative size continues. So again, if Earth were a marble, Jupiter would be almost a meter across. This is our sun. So comets. Are made of rocks cemented together by ice. As they near the sun, the ice begins to melt, giving them the tail, which is pretty much just a collection of steam and dust. Meteor is something when we see a flash of light in the sky. That's a small chunk of debris that burns up as it passes through our atmosphere. That's also known as a shooting star. And then meteoroids are what is left from the dust, the fragments of the asteroids after a collision. So nebula, the collection of gases and floating spaces. This is where stars are formed. There's more to go on that. And this is kind of pictures of our galaxy and the nebula. So if you go to, stars are formed basically when gravity pulls the gases of nebula together and increases the temperature while fusion is happening. So fusion is the combination of atoms or molecules. So there's many types of stars. So we have what happens to a star after it becomes a red giant depends on the star's mass. So there's more about that in the link below. Smaller stars end up as white dwarfs. So our star would end up as eventually this would be the eventual what will happen to our sun eventually in about 5 billion years. And then heavy stars will end up as neutron stars, which is also known as black holes. So the fate of a super heavy mega massive star is a black hole. So this is kind of the summary of a star. So you can use this stages. Relates to part of your notes that you have. And then a galaxy. So a galaxy is a collection of these gravitational bound stars and clouds of dust and gas. And so the approximate size of the Milky Way galaxy is about 9.46 times 10 to the 20th meters. It has about 100 collection of gravity-bound stars and clouds of dust and gas. Supercluster is a collection of galaxies. The universe is then obviously a collection of superclusters or galaxies. And this universe is infinite, but we define it by basically how much is visible to us, and we call this the visible universe. The stellar evolution, so this is more details of what happens to a star. So you have a star's glowing sphere of plasma. So it's not a big ball of fire. So basically there's a bunch of atoms that are fusing together in nuclear fusion that generate heat and energy that way, which makes it glow. So this is what happens in nuclear fission. So you have atoms that combine together and produce energy. So in order to fuse the smallest element, you need to exert enough pressure to heat the hydrogen to millions of degrees. So this is why the sun is really hot. So how does a star implement nuclear fusion? Basically stars are fat. So they have masses that exert a huge gravitational pressure on the core of the star, and the intense pressure can then have enough energy to collide together, undergoing nuclear fusion. Does fusion occur anywhere else? As it turns out, the core of the star is part of the star where fusion occurs. All the light and heat we see from the star ultimately comes from the core. The outer layers are still important, but they apply the necessary pressure to have fusion occur in the center. So fusion is not outside, but it's in the core of the star. Stars are balls of gravitational bound plasma, and so there's sufficient, but before we want to explain also how different stars are different colors and sizes. As you see, so what causes stars to be different colors? They almost behave like perfect black bodies that take in energy from the core and emit large ranges of frequency of light. The warmer the temperature, the bluer the peak, and the cooler the temperature, the redder the peak. So this is how you get different colors of stars. So we basically categorize stars based on their temperature, and therefore it is categorized by color. So as you see here, blue stars are only 28,000 Kelvin, or 28,000 Kelvin, whereas red stars are 2,500. So blue stars are actually the warmest. Our sun is a G. So the temperature of the star is about 5,000 to 6,000 Kelvin. So properties that correspond to bluer stars are hotter, redder stars are cooler, bluer stars are bigger, redder stars are smaller. So the radius of a blue star is huge, whereas the red stars are tiny. So blue stars are actually super bright and redder stars are dim. So redder stars live almost forever, whereas blue stars live fast and die young. So one property, our stars are fat. So then if you think about this, a star with a smaller mass has several important differences compared to a star with a large mass. So if there's more, so a star with key feature is the core when nuclear fusion occurs. If there's more mass in the outer layers, there's greater pressure on the core, resulting in a higher temperature. Whereas if it's a smaller mass, there's less pressure on the core, resulting in a lower temperature. So as mass increases, the lifetime of a star decreases. Greater mass means the core is burning hotter and faster. So it's like it's basically between lighting a candle at the wick and it burns slowly versus throwing the entire candle in the bonfire. The candle burning instantly. The size is based on the energy output of the fusion reaction. So as you see here, so how do stars change over time? So stars are formed in a nebula, and then here's more examples of nebulas. So stars will enter the next stage if the gravitational pressure creates a temperature of at least 4 million Kelvin in the core. At this point, the star is classified as a main sequence star. The star is kept in a delicate balance between gravity trying to collapse it and radiation pushing it outwards. As hydrogen runs out, the energy released from the fusion decreases. The gravity causes the star to collapse. If temperature increases large enough, the core will start fusion again, but this time fuse heavier elements, and the star is classified as a red giant. So basically the next step would be to become a red giant. Stars continue the cycle of fusing an element, running out, and burning a new element if the gravitational pressure is large enough. So this sequence would be helium, carbon, neon, oxygen, and silicon. A star will not burn heavier elements if it does not have the mass to raise the temperature needed for the next stage. Our sun will stop at oxygen. Unfortunately, a star can never fuse forever. If the star has enough mass to essentially, even if the star had enough mass and to get an infinite temperature at the core, there is a limit. Iron is where fusion naturally stops. Iron is the most stable known element, so fusing iron or heavy atoms is not self-sustaining. So red giant, no more fusion. So what happens eventually is the core until it explodes. The resulting explosion depends on how much pressure was compressing the core. So with stars that have a mass up to 3 times our own sun, the explosion of the core is relatively minor. The outer layers create a planetary nebula around the core that remains now called a white dwarf. White dwarfs glow with the leftover heat like the ember of a campfire, but no longer fuse elements and will eventually die and become a black dwarf. For stars up to 15 times as big as our sun, these stars will supernova, and then this remnants are called neutron stars. So the largest stars, more than 15 times our sun, undergo a supernova as well, but the core then undergoes such a huge compressive force that the matter of the core is compressed into a single point, creating what astronomers call a black hole. So remember that the core uses up fuel, the outer layer is still pristine sources of fuel, so when the core explodes, supernovas, the outer layers become future nebula, and the cycle of stars is restart. Alright, so this is the history of the planets and how stars are formed. So if we go to, so I want you to go ahead and just put in a description of each of these things in our solar system. Name the planets. And then this gives you kind of the distance from the sun in millions of kilometers. So this would be 58 million kilometers. This is the time to take orbit, and then go ahead and answer these questions. So based on what I did from the last part of the slides, what happens when a star is born? So go ahead and match up the stages for the stars. And the last part you're going to do is modeling the solar system. So what I want you to do first, so there's two parts. So on the spreadsheet, you guys are going to look up the size of each of these objects. You're going to find the diameter. Make sure you look up the same units for all of them. So if you find meters, make sure you type it in meters. Make sure you understand that scientific notation 10 to the 9th means that there's 9 zeros after the number you see. And then you're going to also look up the distance to the sun. So the sun, for example, is a distance of 0 because that's where the sun is. And so what you're going to do, so you're going to research all these values, make sure all your values have the same units. And so for scaled sizes, for example, you're going to choose a reference object. So let's say I choose Earth. The scale size I'm going to say is 23, and that's going to be centimeters. So if that's 20, if the Earth, we're going to scale it to 23 centimeters, that means I'm going to take the real size of the object. So you're going to take the size of the sun, right, divided by the real size of Earth, and then you're going to multiply by the scaled size to figure out the scaled size of the sun. So for example, over here, if I had Earth is 23, so that if I knew that the Earth is 12,756 and the sun is 1,392,000, I would take the size of Earth divided by the size of sun multiplied by the scale size to figure out the scaled size. Now again, this is still, depending on if this is centimeters, this is still like 25 meters, so that may be kind of big. So when you think back to when you're actually going to make something out of household items, you might want to pick a scale size that might be smaller. And you want to do the same thing for distances. So you're going to look at the distance. So you're going to pick let's say the reference object is going to be Earth again. The scale distance, let's say it's like 1, and I make it 1 centimeter or something. So we're going to scale the distance to the sun based on Earth being 1 centimeter away from the sun. Once you guys do that, so you're going to calculate this. So you're going to you're going to calculate you can pick 2 different references objects, and then you're going to scale the sizes and scale the distances. And then using this information, how we figured out how to scale something, I want you then to create a model of the solar system using household objects. So for example, if you figured out how big a marble is, and say you want your marble to be Earth, you'd have to figure out how big are the fine objects that would correlate to those other objects, and take a picture of all the objects in there, right, and label which one's which. Right here, if you do distances, you can just pick maybe a bunch of marbles and have them all be a certain distance apart based on how you scaled your model. And then that's what you're going to turn in for the assignment. So then once you finish, make sure everything's attached and go ahead and turn it in. Hopefully this helped, and I will be available to answer questions if you have it, and hopefully you're having a great day.